Let's begin. Note 6.5, operations with radical expressions. What are operations? Math operations. PEMDAS, right? That's the correct order of operations. Parentheses first, exponents, multiplication, division, addition, subtraction. And we are going to do operations with radical expressions. Now, we've already simplified radical expressions. We know that if we have like the third root of x to the 12th, we already know that the power goes over a root. Any radical could be changed to a rational exponent. X and the power 12 will go over the root 3. So it's an exponent, that's a fraction. The power goes up on top, the root goes on the bottom. So this answer is actually x to the 4th. So we learned how to simplify that yesterday. We're now moving on to doing operations with radical expressions. So we're going to imagine that radical expressions, we're going to kind of treat them like if they were a variable expression. We know how to combine like terms. What does a variable expression look like when we combine like terms? That's where you have 2x plus 3 of those x's, giving you a total of those 5 x's. Nice and simple. The radical expression, it's the same exact thing. You could combine like terms when they are alike. Now, what do I mean by that? I have 2 of these square roots of 3's. It's like 2x. Plus 3 of those same exact square roots of 3's. It's like 2x plus 3x. It'll be a total of 5 of those x's, but instead of x's, we have square roots of 3's. Make sense? Okay. Now, what if I had x plus y? Could I combine x plus y? No, so you would just leave it, x plus y. They're not like terms. So similar to variable expressions, if you have the square root of 2 plus the square root of 3, you can't combine those because they're not like terms. Okay, you could combine square roots of 3's with square roots of 3's, but you can't combine square roots of 3's with square roots of 2's. They're not like terms. It's like trying to combine an x plus y. You can't do that. So I cannot combine, we said operations. We're going to be doing all math operations. I cannot combine x plus y, but could I multiply x plus y? Yeah. Could I multiply x times y? I'm sorry about that. Yeah, x times y. What is x times y? xy. So likewise, I could actually multiply square root of 2 times the square root of 3. You just multiply them together. But in this case, yeah, square root of 6. And that doesn't really help us on that example. But like, let's say I did have like this one, the square root of 2 times the square root of 8. That works out beautifully. Why is that? Because square root of 2 times square root of 8 is square root of 16, and the square root of 16 is 4. That works out nice and neat. So again, the main point on this video so far is that you could simplify radical expressions kind of like you simplify variable expressions. You could combine them, you could multiply them. Let's do a couple more examples. Right here, am I able to combine these radicals? No. Well, I should say not yet. And why can't I combine 8 of these guys, take away 5 of those? Well, see, because they're different, right? They're different. They need to be like terms in order for you to combine them. By the way, the calculator does all this. As long as there's no variables, you could type it into the calculator and it'll give you your answer. But I want to show you how to do it on paper as well. You see the square root of 45, you could rewrite that. It's not a perfect square number. You could rewrite that as 9 times 5. And when you split the root, you'll get 3 square roots of 5. Yes? And out here we have times this 5. So bring down that times 5. Bring down the minus sign. And you could also bring down the 8 square root of 5 out here in the front. So anyways, what do we really have here? We have 8 square roots of 5 minus 15 of those square roots of 5. And at the beginning, we could not combine them because there were different terms. But if you look at them now they are the same exact term. It's 8 of these guys, take away 15 of those exact guys. It's like 8x, take away 15x. What's my answer going to be? Negative 7 square root of 5. That's right. It's like negative 8x, take away 15x, it'll be negative 7x. You treat them like if they were variables. You could only combine them when they're the same exact variable. You could only combine them when they're the same exact radical. And you could multiply them whenever you want. They don't have to be the same to multiply. Like I said, we could multiply, but we could treat them just like variables. So if I have 2x times 3x, you don't have to copy that down, you already know that. That's going to be 6x squared. 2 times 3 is 6. X times x is x squared. Same thing over here. 2 square root of 3 times 3 square root of 3. You go to 2 times 3 and get 6. And the square root of 3 times the square root of 3 happens to be the square root of 9, which goes back to 3. So you really have 6 times 3. And 6 times 3 is 18. Now you don't have to have the same exact radical to multiply. You could have the square root of 3 times square root of 2. You could have the square root of 4 or the square root of 5 times square root of 7. You can multiply any radical. Let's check this out. Go ahead and copy these 3 down. More examples. So when we multiply on number 1, 2 times 3 is 6. And the square root of 2 times the square root of 8, what's that? Square root of 16. And what is the square root of 16? You really have 6 times 4, which is final answer 24. Like I said, radicals, simplifying radical expressions is kind of like simplifying variable expressions. It's kind of like if you had x times 4 minus x. You just distribute that x to each of those terms and see what happens. In this case, you're going to be distributing the square root of 3. Square root of 3 times 4, what's that? 4 of those square roots of 3. And the square root of 3 times the negative square root of 3. What's a positive times a negative? It is a negative. And the square root of 3 times the square root of 3 is what? Square root of 9. And you could write the square root of 9, or you could already write your answer. What's the square root of 9? 3. So your final answer for number 2 is 4 square root of 3 minus 3. And you know what? They're probably going to write it with the real number first and the root second. So they're probably going to put negative 3 first plus 4 square root of 3 second. And number 3, this is a fun one. When we have a binomial times a binomial, we distribute and then we combine like terms, right? So let's do that. Again, you're treating it like if it were a variable expression, kind of like if it said 3 minus x times 3 plus x. Distribute each term. So when we go 3 times 3, we get 9. 3 times square root of 2, we're going to get 3 times square root of 2, which is 3 square root of 2. And then when we distribute negative square root of 2 times 3, a negative times a positive is a negative. You put the 3 out and the square root of 2 behind the 3. And then negative square root of 2 times positive square root of 2, a negative times a positive is a negative. And the square root of 2 times the square root of 2 is what? Square root of 4, which eventually become 2. Now let's combine like terms. The middle terms, we have one positive 3 square root of 2 and one negative of that same exact 3 square root of 2. It eliminates, it disappears. There's no more square roots of 2 left. And the square root of 4 is what? So what we really have here is 9 take away 2, which is what? 7. A nice, beautiful answer, 7. Does anybody think that this problem looks familiar? Nobody? I'm not even going to ask you what, but it kind of looks familiar, right? To something we did in semester 1. I don't expect anybody to remember this, but does anybody remember where this similar type of math happened? You guys remember complex numbers, imaginary numbers? You guys remember multiplying a complex number with its conjugate? You guys remember the conjugate? It's the same identical binomial. The only difference is the middle sign changes, right? Yeah. And when we did that, when we had a real number and an imaginary number, and when we multiplied the complex number by its conjugate, the imaginaries completely disappeared and we ended up with something nice and beautiful, a regular natural number, right? Same deal here. Whenever you multiply a binomial that involves a radical with its conjugate, the radicals disappear and you end up with a nice, beautiful number. Okay? Now that's going to come in handy when we try to get rid of radicals in the denominators of fractions. We're going to have to multiply by the conjugate. So just keep that in mind. We'll talk about it in a couple of minutes. Actually, let's talk about it right now. It says we do not want to leave a radical or a term with a rational exponent in the denominator of a fraction. Okay? So if you ever have a square root in the denominator of a fraction, you want to get rid of that square root. Even if you have a rational exponent in the denominator of a fraction, you don't want, because a rational exponent really is some type of root. You don't want to leave any type of root in the denominator. So how could we get rid of, let's say, this binomial has a square root of 2 in the denominator. To get rid of a binomial that involves a square root, simply multiply it by its conjugate. Okay? So right here we're going to multiply both top and bottom by the conjugate of 2 square root of, or 2 minus square root of 2. So what is the conjugate of 2 minus square root of 2? 2 plus square root of 2. Perfect. And what you do to the bottom, you must do to the top. So we're going to go times 2 plus square root of 2. So this does take a lot of concentration, a lot of work. Okay, let's do the numerator. 3 times 2 is 6. 3 times square root of 2 is 3 square root of 2. And then distribute the square root of 2 times 2. That's going to be 2 square root of 2. And distribute the square root of 2 times positive square root of 2. A positive times a positive is a positive. And the square root of 2 times square root of 2 is the square root of 4. Does everybody agree with that distribution that I just did? But do you guys agree with it?
Yeah.
All right. Now, let's combine the terms that are alike. The middle terms, they do not cancel out, but I could combine them because they're both the same type of root, which is a square root of 2. Same radical. So 3 plus 2 is 5. So I'm going to have a positive 5 of those square roots of 2. And over here, I have a nice, beautiful 6. And over here, I really have a nice, beautiful what? 2. So 6 plus 2 is 8. So here's my numerator. And I still need to distribute down here and combine like terms. But down here, because I multiplied this binomial by its conjugate, it's going to be a nice, beautiful answer because everything is going to eliminate, the roots are going to eliminate except for the answer. So let's show our work here. 2 times 2 is 4. 2 times square root of 2 is positive 2 square root of 2. Negative square root of 2 times a positive square root of 2, that's a negative 2 square root of 2. Negative square root of 2 times positive square root of 2, that's a negative square root of 4. And again, the middle terms, one's positive, one's negative, they're identical, but they're opposites. They cancel out. And what we have here is a 4 that comes down minus, and the square root of 4 is 2. So 4 minus 2 is a 2 in the denominator. So 2 is all that's left in the denominator. There's your answer. 2 down here. If you wanted to, you could take that denominator and split it into each of those terms. You could put 8 over 2 plus 5 square root of 2 over 2, which would ultimately give you the answer 4 plus 5 square root of 2 over 2. This one is completely correct. I'll accept this. It's 100% correct. But just in case you're taking a multiple choice test and you don't see this, they might write it like that. So you are not going to want to leave a radical in the denominator. You might have to multiply by its conjugate to get rid of it. Now, what if you did not have a binomial down there? What if you just had like 3 over the square root of 2? There's no binomial, so you don't even have to worry about the conjugate, but what would you multiply by? By that same square root value, top and bottom. So your answer would be 3 square root of 2 over 2. Another way of looking at this problem, 3 square root of 2, you could actually look at the square root of 2 as a power of 1/2. Now, I don't really recommend this, but it's a different way of looking at it. If you wanted to get rid of the rational exponent, you'd have to multiply it by a value that'll make that a whole. So if you were to multiply by 2 to the 1/2 power, then your 2 to the half times 2 to the half, if you have the same base and you're multiplying, what do you do with the exponents? Add them together, right? When you're multiplying two terms with it, like if I say what's x squared times x to the third, it'd be x to the fifth. Where you have 2 to a certain power times 2 to a certain power, you combine the exponents and you'll get 1 whole. 1/2 plus 1/2 is 1 whole. So your final answer would be 2 on the bottom to the 1 whole, so you don't need 2 to the 1. But up on top, you have 3, 2 to the 1/2, which is really square root of 2. So you see how we end up with the same answer, just looking at it differently? We're not going to really need this skill right now. It's more for the next section. But I did want to mention it, that you may also have to get rid of any rational exponent by multiplying a value that'll make it a whole. That'll make it whole. So like let's say I had 5 over x to the 2/3 power. That's technically the third root of x squared, right? Now you don't want to leave the third root of x squared in the denominator. You don't want any type of root. In this case, you don't want any type of rational exponent. So what would I have to multiply both top and bottom by to make it a whole? X to the 1/3, exactly right. Put a 1/3 right there and a 1/3 right there. That way, when you do this multiplication, you're really adding exponents, and 2/3 plus 1/3, that'll give you 3/3, which means that your answer will just be x on the bottom. And up on top, you'll have a 5 third root of x, or 5x to the 1/3 power. But that would be your final answer right there. So again, that's more for future sections, but it's something very important that we will need to know anyway. So whenever you do have a rational exponent, you can multiply it by something that'll make it whole. And of course, what you do to the bottom, you do to the top. Let's actually look at our worksheet for today. So this assignment's all jacked up. First of all, there's not enough space to really show all our work on this, all right? Not only that, the calculator will do the ones that don't have variables in it. So I canceled out 1 through 5, 1 through 6. We're doing 7, 8, 9, 10, 11, even though 11 could be done on the calculator. Skipping 12, skipping 15, skipping 10 through, what is that, 16, 17, and 18. Skipping 20. Yeah, I apologize. Skipping 29 and 32 and 27.
20? Wait, 20? 20, 29, 27.
All right, so if you look at 7 through 10, all of those have radicals, and we could split those radicals to each of the terms on the inside of the radical, or each of the items on the inside of the radical. So which one do you like to see, 7, 8, 9, or 10?
Doesn't matter.
Doesn't matter, pick one. 7.
8.
Okay, if we go for 7, let's split that third root to each of the terms. So we split that third root to each of the terms, and this could be done on the calculator, or you could think about it. 5 times 5 times 5 is 125, so your answer is 5. And then right here, we need to use the skill set that we learned yesterday, the power over root. So 6 divided by 3 is 2, so you will get a 5t squared. And right here, if you try it, 2 divided by 3, you get a fraction 2/3. So it's kind of pointless to rewrite this as w to 2/3 because you can't reduce 2/3, you can't divide 2 by 3, so you're kind of stuck. The only reason you would change it to a w to the 2/3 is if they said write your answer as a rational exponent. But they don't say that, so they're going to leave it as a radical. So just let's leave it as a radical, the third root of w squared. So there's your answer for number 7. And all of these are done that same way. Would you like to see any other one? 7, 8, 9, 10? Or so on number 8, let's split up that fourth root to each of the terms. And then when we simplify this, the calculator, I believe, will do this for us. Maybe not, right? I don't know. I know they simplify square roots. I'm not sure if they'll do fourth roots. Does anybody have a calculator?
Yes, it is like 2.6.
So they give it to you as a irrational value, right? A crazy decimal. So yeah, let's do this by hand. You see, I would like this to be like, let's say 3 to the 4th. Because if it were 3 to the 4th, the fourth root and the fourth power would eliminate and I'd just have a 3 left over, right? But obviously 3 to the 4th is definitely not 48. That's way too big. 3 times 3 is 9 times 3 is 27 times 3 is way bigger than 48. So maybe 2 to the 4th. What is 2 to the 4th, guys? 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, so 16 times 3 is 48. So check this out. We're going to take that 48 and we're going to rewrite it as 16 times 3. But instead of 16, I wrote it as 2 to the 4th. Why? Because I wanted a certain number to the 4th power, so it'll eliminate with that 4th root. So technically, this 48 is right here. And when I split the 4th root to each of those, the 4th root of 2 to the 4th will eliminate, and it'll just be 2. Or you could think of power over root. 4 divided by 4 is 1, so you will get 2 to the 1, which is just 2. Are you with me? And the fourth root of 3 is going to stay as a radical. Okay? Now over here, this guy, v to the 8 and the fourth root of v to the 8th, power over root, what do I end up with? I end up with v to the what? Squared, that's right. And the last one, this one's kind of interesting. If I say power 13 over root 4, I'll get z to the 13 divided by 4. That's improper fraction. 13 divided by 4, what will that be really? Z to the what? 3 and the remainder of 1 over the original 4, 3 and 1/4. Are you with me? Now we're going to use rule 1 of exponents backwards, where if I did have z times z, that would give me z squared. I'd add exponents, but we want to add this exponent with this one to give us the 3 and 1/4. So we're going to split it and put the 3 on this first z and the 1/4 on the second z. So what that does is give me a nice z to the third, okay? And z to the 1/4, that's going to stay as the fourth root of z. So what do I have here? Let's write our final answer to number 8. We have a nice beautiful 2. We have a nice beautiful v squared. We have a nice beautiful z to the third. And then we have the fourth root of 3. But we also have the fourth root of z, so let's put those together, and it'll be the fourth root of z, or 3z. So here's my final answer, 2v squared, z to the third, fourth root of 3z. I said, dang, we're having fun. Right? No. Okay. So on all those, you split up the root and you mess with it to get the better answer. Let's go to one that we have to actually distribute. There's a bunch where we have a binomial times a binomial that involve roots, okay? So which one should we do? 21, 22, 25, they're all a binomial times a binomial that involve a root. 23, I don't know, what do you guys say? 22? 22 is pretty easy. Let's write that binomial 2 times. And then it's a question of distributing and combining like terms. 3 times 3 is 9. 3 times negative square root of 7, a positive times a negative is a negative. And 3 times any root will be 3 with that same root. And then we distribute that negative root times that positive 3. So that's going to be a negative 3 square root of 7. And negative square root of 7 times negative square root of 7. A negative times a negative is a positive. And the square root of 7 times the square root of 7 is the square root of 49, which will later become 7. Let's simplify it. The negative 3 square root of 7 with the negative 3 square root of 7, it does not cancel out, but I could combine them, and it'll give me a negative 6 of those square roots of 7. And then out here, I have a nice, beautiful 9, and over here, I have a nice, beautiful, what is that? 7. So what's 9 plus 7? 16. Normally, they put the nice, beautiful answer in front of the radical, so that's your answer, 16 minus 6 square root of 7. So distributing, combining like terms, that's what it's all about. Same with the rest. And again, down here, we're going to have radicals in the denominator, and you do not want to leave a radical in the denominator. You're going to have to multiply by its conjugate to get rid of it. So on number 33, let's take that 2 minus square root of x and multiply by its conjugate 2 plus the square root of x. So this is a pretty long problem because you're going to have to do it both to the top and to the bottom, and you do have binomials on both top and bottom, right? So let's do the top one. That's probably the more challenging one. 3 times 2, that's 6. 3 times square root of x, what's that? Come on, guys. Help me out here. 3 times square root of x. 3 times square root of x, right? You can't do it, just rewrite it. How about positive square root of x times 2? 2 times square root of x, that's right. And how about positive square root of x times positive square root of x? Positive square root of x squared, right? So positive square root of x squared. So what does that become at the very end? Just x. Or you could have even written it as square root of x squared, and it would still just be x. Let's combine like terms, the ones in the middle. The 3 of those guys with 2 more of those guys, that gives you 5 of those radicals. And we do have 6 that we're just going to write. And this was a positive 5, square root of x. And this guy over here, we said that the square root and the square eliminate, so we end up with just the beautiful positive x. So there's my final answer for the numerator, 6 plus x plus 5 square root of x. Let's do the denominator now. The denominator will be easier because when you multiply a binomial by its conjugate, you end up with a nice, beautiful answer. Check it out. 2 times 2 is 4. 2 times square root of x is 2 square root of x. Negative square root of x times a positive 2, a negative times a positive is a negative, and we have 2 of those square roots of x. And negative square root of x times a positive square root of x, a negative times a positive is a negative. And the square root of x times square root of x, we could write it as the square root of x squared. Multiply x times x, you get x squared. The middle terms, one's positive, one's negative. They're the exact opposite values. They're going to cancel out. We have a nice, beautiful 4. And what do we have over here? The square root of x squared, that just becomes an x. The square root and the square eliminate themselves. You could even think of it this way, power over root. That'd be x to the 2 over 2. That'd be 1, x to the 1. So you really have 4 minus x as your denominator. So you put 4 minus x as your denominator. And ladies and gentlemen, we're done. That's your answer for 33. It had a variable in it. So I trust that with those examples, with all these notes, you should be able to go through and do the rest of these. That's what we're doing for the rest of the class. That's what you guys are doing for homework. If you don't finish, the answers are on the back. Please check your answers as you go.